Okay, so this is starting off Chapter 6, problem number 20. And what we're doing in the next couple of problems is we're just verifying that this particular equation, the differential equation x y prime minus 2y is equal to x cubed e to the x, that's the differential equation. We're asked if this particular case, y equals x squared times e to the x, if this is a solution to this differential equation. So basically what we do is we have y already, and we calculate y prime by taking the derivative, and then we substitute in for y prime and y, and if this, once we simplify it, that the left-hand side equals the right-hand side. And we verify that, and then we say that this is a solution to that differential equation. So the first step here is just to calculate y prime. And y prime is dy dx. We're taking the derivative of this with respect to x. We're taking the derivative of this with respect to x. So we have a product, so we use the product rule. And so the derivative of x squared e to the x is going to be the first term times the derivative of the second term. The derivative of e to the x is just e to the x, so that part doesn't change. Then you take the derivative of the first part, which is the derivative of x squared is 2x, and you leave the second part the same. So that is the derivative of y prime. So we can kind of write that as x squared e to the x plus 2x e to the x. That's the derivative of this using the product rule. Now we substitute in for y prime, we put that in there. For y, we plug that in and see if after we simplify we get x cubed e to the x. So the first term is x times y prime, which is going to be x squared e to the x plus 2x e to the x. So we're just substituting that in here. Go back to the original equation, then we have negative 2 times y. Y is x squared e to the x. And ultimately we want to see if that's equal to the right-hand side, which is x cubed e to the x. So we're just going to use the distributive law to property to just multiply x times each one of these terms. So we're going to get x cubed e to the x. Here we have x times 2x e to the x is 2x squared. 2x squared e to the x. We just multiply 2 times that, so we get 2x squared e to the x. And let's see if we have some common terms we can cancel out or simplify. Well, here we have plus 2x squared e to the x. We have negative 2x squared e to the x. Those cancel out. So all we have left is x cubed, the first term, which is x cubed e to the x. And that equals the original right-hand side of the differential equation. And since these are the same, then the equality is satisfied. And therefore, because of that, we can say that y equals x squared, whatever the original thing, x squared e to the x is a solution to that original differential equation. Okay, so that's how that works. Okay, so we're going to do one more of this group, which is verifying that the result, the equation, in this case for 23, that y equals the natural log of x is or is not a solution to the differential equation x times y prime minus 2y is equal to x cubed e to the x. So just as previously, we're going to be able to substitute y in here, and then we're going to calculate y prime by taking the derivative, plug it in there, and see what we get. So y prime is just going to be equal to 1 over x, because the derivative of the natural log of x is 1 over x. Now we plug that in, and so for y prime we put 1 over x. We say x times 1 over x. And we have negative 2 times y, but y is times the natural log of x. And the question is that equal to x cubed e to the x? So we'll simplify. So we get 1, x divided by x is 1. So we get 1 minus 2 times the natural log of x, and that does not equal x cubed e to the x. And therefore, since this is not an equality, y equals the natural log of x is not a solution to the differential equation. So it either is or it isn't. And I was just going to check, look in the answer book here. 99% sure we're okay, but let me just pause it for right now. Okay, so I've checked the book, and that is the correct answer. It is not a solution. Problem number 33. So this is basically kind of the same thing that we just did in 20 and 23, except first thing is problem number 33 is a second order differential equation. And so we're going to verify that the solution is valid no matter what C1 and C2 are, but then we're going to find the particular solution by using the 2 initial conditions. We have 2 initial conditions because it's a second order differential equation. If it was a first order differential equation and we just had y prime, then we would only have 1 initial condition. So if you look at 31 and 32, you'll see that there's just 1 initial condition because there's just y prime, whereas 33 and 34 have a y double prime, which means it's second order, and they have 2 conditions. Okay, so the solution that they say, this is the solution to the differential equation. And the differential equation is y double prime, which is the second derivative, plus 9y is equal to 0. So just like we did in the previous problems, we're going to calculate the first derivative, and then we'll calculate the second derivative to get this part. We'll plug it in and verify that this is true, given this being a solution. So to be able to get the second derivative, we have to do the first derivative first. Okay, so when we first take the first derivative, we're going to get, using the chain rule, this 3 is going to come out. So we're going to get 3 times C1, which is just a constant, times the derivative of the sine, which is the cosine. So we get the cosine of 3x. And then the second part, we're going to have, again, the 3 is going to come out because of the chain rule, because that argument is something other than x. So we're going to have 3 times C2, and the derivative of the cosine is negative the sine. So we get negative the sine of 3x. And that's our first derivative. I'm going to rewrite it where I'm going to move that negative sign out front. So it would be negative 3 C2 sine of 3x. So that's the first derivative. Second, but take the second derivative, y double prime, we just take the derivative of the first derivative. So it's just like we're doing here. We have 3, when we use the chain rule here, this 3 is going to come out again, so we'll get 3 times what we had originally, which was 3 times C1. The derivative of the cosine is negative the sine, so we get negative the sine, and it stays 3x. We don't change the argument. Okay, the second part, again, we get the 3 coming out. So we're going to have 3. This 3 comes from the chain rule here, so that comes out. We have our 3 that's originally there, and we multiply by the derivative of the sine, which is the cosine. So we get the cosine of 3x. Don't change the argument. So again, we can bring the negative sign out, and we can complete this multiplication. So we have negative 3 times 3, which is going to be negative 9, times the sine of 3x. And here we get negative 3 times 3. There's no additional negative sign, so it's going to be negative 9 cosine of 3x. So those are the two derivatives. Now we plug the value for y into there and the value for y prime into there. So y prime is negative 9, the sine of 3x, minus 9 times the cosine of 3x. And we add 9 times y, which is here. So we get C1. Sine of 3x, let me smooth this over a little bit, run out of space, plus C2 cosine of 3x. That's from here. And that is supposed to be equal to 0. If this is a solution and we plug it in, we should get that equality. So what you can see is we have negative 9 sine of 3x plus 9 sine of, pardon me, I forgot the C1 part here. Sorry. So let's go back and fix that. Negative 9 C1, negative 9 C2. I knew I messed up because things weren't canceling out. So you get a negative 9 C1 sine of 3x plus 9 C1 3. So this cancels out with that, and the same way with the second term. So because these are equal to each other except in the negative, the left-hand side becomes 0, and because the equality is satisfied, y is equal to C1 sine of 3x plus C2 cosine of 3x is a solution to that particular differential equation. Okay, so we proved that it's a solution. And we verified is the general case. It's true. Now we want to find the particular solution. So our initial conditions are when y equals 2, y equals 2 when x is equal to pi over 6, and when y prime equals 1, when y prime equals 1, when x is equal to pi over 6. Okay. So what I'm going to do is I'm going to actually try to figure out the best way of doing this. I'm just going to extend the page. So basically what it says here is when y equals 2, so we go back to the original equation, y equals 2 when x is equal to the pi over 6. So all I do is I put y in to the original equation, I put x equals pi over 6. Let's go ahead and just simplify this before we do the next part. So we get 2 is equal to C1 sine, well, 3 divided by 6 is 1/2, so we get pi over 2 plus C2 cosine of pi over 2. Okay. The second one is we plug it into the first derivative. So we know y prime equals 1, so we put 1 on the left-hand side. We have 3 times C1 cosine of 3 times x, which is, again, pi over 6, plus, or minus, because the minus right there, minus 3 C2 sine of 3 times pi over 6. And again, before we do anything here, we're going to multiply out the term in the parentheses. So we're going to get pi over 2 again. minus 3 times C2 times sine of pi over 2. So so I'm going to add another page at this point. So we got two equations and two unknowns, but it's actually easier than that because the sine of pi over 2, if you think about the unit circle, pi over 2 is here, and the sine is the y value, so the sine of pi over 2 is 1, and consequently the cosine of pi over 2 is 0. That's the x value of the coordinate in the unit circle. So you get 0, so we can plug those in here. So plugging it into the original equation, we get 2 times C1 times the sine of pi over 2, which is 1, plus C2 times the cosine of pi over 2, which is 0. So we'll get 2 is equal to C1. This goes out. This is just 1 times C1, which is C1. So C1 equals 2. And then you can do the same thing for the first derivative. So we get 1 is equal to 3 C1 cosine of pi over 2, which is 0, minus 3 from here times C2 times the sine of pi over 2, which is 1. So that goes out. So we get 1 is equal to negative 3 C2. And therefore, C2 is equal to negative 1/3 by dividing both sides by negative 1/3. So those are our arbitrary constants for this particular solution. So all we have to do now is plug that back in to the original equation to get the particular solution. So our particular solution is y is equal to C1, which is 2, times the sine of 3x plus C2, which is negative 1/3, times the cosine of 3x. And this is problem number 33, and the answer is 2 sine of 3x minus 1/3 cosine of 3x. So that works out. Okay, just double checking to make sure I have the sound on. Okay, so we're at problem 39 now. 39 and 42 are just solving differential equations that we've actually been solving. We actually did that for some of the homework problems, and I think it's on the test, so there's really nothing super new here. So we have problem 39 is dy dx is equal to x divided by 1 plus x squared. So dy dx is the same as y prime. So it's a differential equation. It involves y prime. It doesn't involve y, which makes solving the equation much easier. So when we have that situation, we can rewrite the derivative in this form, which is originally just is dy dx, which represents taking the derivative of y with respect to x. But what we do to solve the differential equation is we make that in the differential form. So it becomes, instead of dy, the derivative with respect to x of y, it just becomes dy over dx. And so at that point, we can multiply both sides by dx. And what we end up with is all the terms involving y on this side, all the terms involving x on this side, and we use a process which we'll call separation of variables. If you can do that, where you can get everything separated like that, then you can just integrate both sides. So we have the integral of dy is equal to the integral of x over 1 plus x squared dx. And the integral of dy is just y. The right-hand side, we would use u substitution. How would we do that? Well, let's just move this over a little bit and think about that. So what is the integral? So we're going to do the left-hand side. Well, what we do is we would say u is equal to 1 plus x squared. And therefore du is 2x dx. this go to 0, and then we get 2x to the first power, which is just x times dx. And we go to the original equation and look what we have. Well, we have x dx. But we can also just solve for dx. So dx is going to be equal to, no, actually, that's not what I want to do. I want to do what's in the original equation, which is x dx. So to get x dx by itself, we divide both sides by 2. So x dx is equal to du divided by 2. So then we make that substitution. Because it's an indefinite integral, we don't have to worry about changing limits because there are no limits. So we get x dx becomes du over 2, and then we get this denominator is u. So we integrate that. The integral of du over u, this is the same, that we can factor out the half, so let's do that. 1/2 the integral of du over u, which is equal to 1/2 the natural log of the absolute value u plus some arbitrary constant c. And then we substitute u back in. So we get 1/2 the natural log of the absolute value 1 plus x squared plus c. Okay, so that's the right-hand side, and the left-hand side is just y. So there it is, and that is our general solution to the differential equation. It's general because we have an arbitrary constant c. To get a particular solution, we have to say y of some value of x is equal to something. So let's just do that. It's not in the problem, but just to, if I said that at x equals 0, y equals 3, you would put 3 on the left-hand side. You take 1/2 the natural log of the absolute value of 1 plus 0 squared plus c, and then you'd have 3 is equal to 1/2 the natural log of 1. Well, the natural log of 1 is 0, and so you get c is equal to 3. And so with this initial condition, the particular solution would be 1/2 natural log of the absolute value of 1 plus x squared plus 3. So when you plug x equals 0 in here, you get y equals 3, and that satisfies it. So this is our particular solution. This is our general solution. And that was problem number 39. So that is correct. Okay, we're going to do one more of these simple differential equations, and we're going to do find the general solution. And the problem we're looking at is 42. So our differential equation is dy dx is equal to x cosine of x squared. So it's not the cosine squared of x, it's the cosine of x squared. Again, dy dx is the same as y prime. So our differential equation is y prime is equal to x cosine of quantity x squared. And so we have an equation that involves y prime. Y is not involved, but it could be involved. But because y is not involved, it's a simple differential equation. We break it up into this terminology. We make it into a ratio of differentials, and we say that we can then write the equation as this. And then we integrate both sides. So the right-hand side, left-hand side just becomes y, and the right-hand side just becomes the integral of this integral, which we've learned to solve last semester. So how do we solve this right-hand side? Can't tell my right from my left. Well, in this case, again, we're going to use u substitution because we don't have an integral that looks like that in our table. But if we make the substitution where the argument of the trig function is u, which u is going to be x squared, and we calculate du, we'll get is going to be 2x dx. So that's, and we look back at original differential equations and say, do we have the rest of the stuff here that we can combine this term with that term and get that? Well, not exactly, but again, we can solve for what we have. So by dividing by 2, so x dx is du over 2. So we can then rewrite the right-hand side as the cosine of u times x dx, which is du over 2. We factor out the 1/2, and so we have the cosine of u du. The integral of cosine of u du is equal to the sine of u plus an arbitrary constant c. And so we'll have 1/2 the sine. Now we can substitute back in, so we get 1/2 the sine of u. U is x squared. And so that is our final solution. That's the solution, general solution to our differential equation. And I'm just checking to make sure it's correct. Okay, so this is problem number 71. So this is using Euler's method. And Euler's method basically, as we talked about in class, is you take the value of the derivative at a point in time or a point in space. And you know what the initial coordinates of the initial point are, and then you estimate what the next point is by assuming the slope remains constant during that time period. So let's just write what's going on here. Y prime is equal to 3x minus 2y. And we have our initial condition, which tells us where we start. So y of 0 is equal to 3. So when x equals 0, y equals 3, we're going to take 10 steps in space, and we're going to have a step size of 0.05. So those are our conditions. I'm going to write these down on my sheet of paper so I don't have to come back. So we're going to do this in Excel. And rather than doing this, well, what I should do is we'll do it separately. We'll do it here for one time, and then we'll go to Excel, and we'll then do it from there. So let me make up a table which will include x and y, y prime, delta y, and I think that's all we need. So we're gonna do a physical table, and then we'll do it using Excel, which is basically a table. So we're going to have x, y, we're going to have y prime, and then we'll calculate delta y. And our initial value of x is 0. That's from here, and our y value is 3. And y prime we evaluate by using the differential equation, which is going to be 3x minus 2y. So if we evaluate the derivative at x equals 0, y equals 3, because this derivative is actually a function of both x and y, we get for x we put in 0, and for y we put in 3. And we'll calculate, I'll go to 0, and we'll get negative 6. So y prime here is equal to negative 6. So that's the slope of this function at x equals 0, y equals 3. And then our delta y we calculate, let's add a page. So our delta y is going to be equal to our original y value. So let's call that, we'll just say it's y0. plus y prime times delta x. Well, in this case, delta x is equal to h, which is equal to 0.05. Y prime we just calculated. Y prime at 0 is -6. So the estimate of delta y is equal to y0, which is the original value of y, which is 3, plus y prime, which is -6, times delta x, or h, which is 0.05. And so that's 3 minus 6 times 0.05 is 0.0 or 0.3. So the second part becomes 0.3, so you get 2.7. Did I do that right? Oh, no. Okay, sorry. Delta y is just y prime times delta x. So let me fix that. So delta y is y prime, which is -6 times delta x, which is 0.05, which is going to be -0.3. So that's delta y. That's how much y changes. So our new value of y, we'll say y1 is equal to y0 plus delta y. So y1 is equal to y0, which is 3, plus delta y, which is -0.3, which gives us 2.7. So now we can fill this in. So delta y is -0.3. X, the new value of x, so we'll say x1, is equal to x0 plus delta x, which is the same as x0 plus h, and that is going to be equal to 0, which is the original value of x, plus delta x, which is 0.05, and so we get 0.05 as x1. That's our first step. So we put that in the table, 0.05. Y is going to be equal to, we just calculated here, 2.7. And then you continue, you do that again. So you would calculate a new value of y prime by going up to wherever it is here. And so let's do that. So let's say y prime at x equals 0.05 and y is equal to 2.7. All we do is then plug it back into here. So you get 3 times 0.05 minus 2 times y, which is 2.7. So I'm just plugging it in here, the x value and the y value. And I'm going to calculate that. So I need to get my calculator. Okay, so we get 3 times 0.05 minus 2 times 2.7. And so the slope, y prime, at those values of x is -5.25. So that goes in here, -5.25. And then we calculate delta y. Delta y at step 1 is equal to y prime from the previous calculation times delta x. And so we get -5.25 times delta x, which is still stays the same. That doesn't change. So we get -5.25 times 0.05. And so delta y is -0.2625. So what you see is as x increases, y decreases initially. As these two change, y prime gets smaller, so the slope gets lower. It's still negative, but it's less negative. And the delta y becomes less negative because y prime is less negative. Okay, you can continue this on and you'll get some kind of solution. So we're going to do this in Excel instead now. So I'm just going to create a spreadsheet here for you. and I'm going to change it. Okay, so we're going to stop sharing that. We're going to start sharing Excel. Okay, so here's Excel. It's a spreadsheet, and the cells we enter basically the things that we had in the columns in the table previously. So cell A1 is, we got over in this class, the columns are represented by letters, the rows are represented by numbers. So we're going to put our column headings here. So this is the X value, this is the Y value, this is Y prime, and this is delta Y, our change in Y. And let us, okay, that's good. So our initial X value was 0, the initial value, Y value was 0, was 3. So here we enter the equation for Y prime. To enter an equation, put equals. So we have equals, and the equation was 3 times X. Rather than putting X in there, we go over to the cell that represents the X value, which is A2, and we subtract 2 times Y, which is the value in this cell. And we take a right parenthesis. We actually didn't need the parentheses, but the delta Y. So again, we get Y prime is equal to -6, which is agrees with our table. And delta Y is just equal to Y prime times delta X, which in this case is 0.05. So that's our delta Y. So our new value of X is our old value, is equal to our old value of X plus delta X, which is 0.05. So you can see what's going to happen is we're going to increment X by 0.05 each step. Our value of Y is our old value of Y plus delta Y. So we say B2 plus, and then we move our cursor. We can just click on the cell, or we can use the arrow keys to get to this point. And so we get 2.7, which is what we got previously. Now it turns out, if we go up to cell C2, we have the equation, which is still appropriate. And if I can copy this equation by highlighting the cell, going down here to the right-hand lower corner, see how it changes from a big plus sign to a small plus sign. And I just click on the corner, so it's still a small plus sign. I drag it down. And what that does is it copies the equation, but it increments the cell. So this equation says A2, B2. This one says A3, B3. So it increments, and it'll continue to do that if I continue to copy it. Likewise, we can do the same thing with delta Y. It has C2 times 0.05. That's the delta Y here, but I want to use this delta Y, so if I copy this equation by, again, going to the lower right-hand corner, wait till it turns from the big X to the small x, and drag that down. You see you get 0.2625. And that's the table as we had it constructed at this particular point. Now, all we have to do, because these are all incremented automatically, I'm adding 0.05, I'm calculating a new value of Y from the old values. I should be able to copy all of these equations. So if I go here and I highlight, so I click on the left cell and then I drag until I have all 4 cells highlighted, and I go to the corner, it's going to copy each one of these cells down, and everything will get copied automatically. And if I go down, I think 11, actually I want to go one more, 12. You see I started at 0 and I've ended up at 0.5, which is 0.05 times 10. And you can see that the Y value has decreased. The derivative is getting closer to 0. The delta Y is getting less. So that's the problem. Let's go ahead and highlight it and kind of extend it down further, because we're going to plot this thing, see what it looks like. Okay, so what the solution is, what is f of x is y, is the y value, and we usually plot f of x versus x. So to make a plot, what we're going to do is we're going to click on the upper cell, X, and we're going to drag it so we highlight all the cells. So we're going to plot X versus Y, see what the solution looks like. Then we go up to the menu here. We're going to click Insert. And we can insert all kinds of charts, and we're going to choose Scatter Chart. So this column, line, pie, bar, area, scatter. And we're just going to pick this one up in the upper left-hand corner. And so this is our solution. This is X, this is Y. And I'm going to go up here. If you look, you'll see up in the right-hand corner it says Move Chart. So we'll go up here. And what that'll do is it'll create a whole new spreadsheet if I do that. So I'm going to click New Sheet. What that's going to do is move this graph out of the way of the data, and it's going to put it on a separate sheet. So I can change the name if I wanted to. I'm just going to leave Chart. So I go OK, and so here's the solution. Almost looks like a parabola. It's not exactly, but it looks like it. This is the x-axis. This is the y-axis. And this is the solution to the differential equation. So all I do is plot x versus y. And you can see what happens is, as x gets greater, y gets smaller until you get to here, and then it changes direction. The derivative is negative, 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 negative until you get to here, and then it's positive. So if you can see around 0.8, the derivative starts to be positive. At this value of x, this value of x, and this value of y, the equation for the y prime gives us a positive result, and then it starts to go. So we can see that in the data as well. See here how the derivative it's always negative until it gets to here at 0.8 x value, a y value of 1.148. It changes to a positive slope, and then it starts to go up, and the delta y becomes positive. Okay, so that's how it works. Okay, last problem in this section is 79, which is similar to 71, except it's a word problem. But basically we have a differential equation, we have initial conditions, and we're asked to use Euler's method. And then we're comparing it with the exact results, so we're going to use Excel to do this. So basically what we have is y prime is equal to minus 1/2 y times minus 72, where y is the temperature, and y prime in this case is dy dt instead of dy dx because we're doing a time thing. So the same, what we have, the initial condition is that at t equals 0, y is equal to 140 degrees Fahrenheit. So that's our initial, that's called an initial condition. And we're going to do a numerical solution. So we're going to make up a table just like we did in the previous problem, which had 3, let's do 4 this time. I think it was 5. So the table consists, the first column is going to be the independent variable, which is time. The second column is the dependent variable, which is the temperature, which we're going to call y. We're going to calculate the rate of change of the independent variable with respect to the dependent variable with respect to the independent variable. This is y prime. We'll calculate delta y. And actually, I don't think I need that extra column, but we'll leave it there just in case I have something I want to put in there, but that's all we need. So at t equals 0, y is equal to 140. And we're going to use delta t, or they call it h again. Let's call it delta t. Delta t is equal to 0.1, and it's going to be seconds. So we're going to calculate y prime from this equation. So we'll do it at first. So y prime at t equals 0. So it's 0, comma 140. T equals 0, y equals 140. Notice this doesn't have a t on this side. So it's different than the previous problem where we had both variables. So it's negative 1/2 times y, which is 140, minus 72. And if you plug that into your calculator, you get negative 0.5 times the quantity, 140 minus 72, and that's negative 34. So that's the slope, negative 34. So delta y is equal to y prime, in this case, times delta t, because it's y prime is dy dt, and if I multiply delta t, I get an approximation for this shape. So delta y is equal to y prime, which initially is negative 34 times delta t, which is 0.1. So you get negative 3.4. So it's going to be delta y is negative 3.4. Okay, so our new value of t is, we increment it just like we did before. So we're going to go by tenths of a second. Delta y, we are going to take our old value of y. So let's say y sub 1, which is we'll call this 0. These are step numbers. We can call like n. So y sub 1 is going to be equal to y sub 0 plus delta y. Y0 is the temperature, and then we add delta y, which is negative 3.4. So if you take 140 minus 3.4, you get 136.6. 136.6. Okay, now you calculate y prime at step 1, which is a function of the time, which is now 0.01 times, and then of y. In this case, the time step doesn't come into the derivative, so it's all it is negative 1/2 times 136.6 minus 72. Just plugging in here, so we have negative 0.5 times 136.6 minus 72, which is negative 32.3. Negative 32.3. Delta y is equal to y prime times delta t. So I get negative 32.3 times delta t, which is 0.1. And so that's going to be negative 3.23. Okay, so now to get our new y, we just add this to that. So we'd say y sub 2 is equal to y sub 1 plus delta y. We can say delta y sub 1, because that's step 1. So you get 136.6 plus a negative 3.23. So 136.6 minus 3.23 is 133.4. 133.4. And then you could calculate, you can go to the next step. But this gives you the first couple of steps. And what we're going to do is we're going to go to Excel now, and we're going to fill this all out. Okay, so here we are. So again, we use the first row to put in the title. So we have the independent variable, which is t. We have the temperature, which is y. We have y prime, which is the slope. And we have delta y. At t equals 0, the temperature was 140. And the slope is just is negative 0.5 times the temperature minus 72. 72 is the ambient temperature. Okay, that's where that comes from. And so you'll continue to have a slope until B2 equals 72. And you get no slope, and it just kind of levels out. Okay, so we get negative 34. And then delta y is equal to y prime. So I go over here and I highlight the y prime value at t equals 0. And I multiply by delta t, which is 0.1. So I get negative 3.4. Okay, now the time we increment, take the original time plus 0.1. The y value is incremented. We take the old value of y, so we highlight cell B2. We add delta y, push enter. We get 136.6. And again, we can copy these formulas down because we're not referring to, we're just referring to stuff on each row. So we take this thing, go to the lower right-hand corner, drag it down. We get negative 32.3 is y prime, and delta y is just y prime times delta t, which is 0.1, and you get negative 3.23. And if I were to copy just these two cells down, I would get exactly what I have in the stuff we just did. Okay, see how the time is incrementing in equal steps. Y is not changing equal steps, it's based upon the slope. Okay, I'm going to go ahead and copy these two down as well. And so to get the rest of the solution, I can just highlight this whole row, grab the lower corner. When it changes to the small plus sign, just drag it down. And let's go down like, okay. So you can see the temperature starts here at 140. It decreases most rapidly at the beginning, and then the decrease here, the fourth column, starts to get less and less and less. And I'm going to drag this out a little bit further. So I'm going to keep copying these equations. Let's go down to 200, all the way down to 100. That'd be 200 seconds. So it's probably right about there. Or not 200 seconds, 20 seconds. Okay, so that's just copying the formulas down. Again, you can see how the time increments by tenths. Y changes relative to delta y, and as delta y gets smaller, this changes less and less. Okay, so now we're going to plot it. So we, again, go to the upper left-hand corner where T is, and then we drag and highlight these two columns, which are the time and the temperature. The one thing we can see here is that we're approaching 72 because as we get closer to 72, the derivative becomes smaller, and therefore the change becomes smaller. Okay, we go up to Insert, up the top here, Insert. Come over here to Scatter, Plot. Choose the one right here, the upper left-hand choice, and there it is. We go up to the upper right-hand corner, choose Move Chart, click on New Sheet. We'll leave the title same. So the x-axis is the time, and the y-axis is the temperature. So the object starts out at 140 degrees Fahrenheit. It cools off rapidly initially, and then it cools off less rapidly. So things like a coffee cup or dropping a hot thing in a cold bath of water, you'll see the temperature behavior like this. It'll cool off rapidly initially, and then once it gets not so warm, the difference between the temperature and 72 becomes smaller, and therefore the slope becomes smaller, and you end up reaching a constant value of 72 in the long run. A horizontal asymptote would be y equals 72. Okay, so that's the solution.